So the next thing we want to do is look at this business of combining experiments, right, which are known to be physically independent. So all of you will have this intuitive idea, right, that is what I checked with you in the beginning of this lecture, or everyone understands physically independent means independent somehow. If you toss two coins, right, there is no reason that one coin should affect the other at all, right. So how do you formally therefore combine independent experiments, right? So physically independent experiments will always give you statistical independence, right. Let me just say physical independence always implies statistical independence, right. Statistical is going to be our adjective to indicate independence in the probabilistic setting, right, the specific, the word and the meaning connotation that we associate specific to all of this. Physical independence obviously is any two things which may or may not be probabilistic, which are, right, done independently or which happen independently of each other, right. So supposing I have two physically independent experiments, right. Omega 1 and omega 2, right. Now again we are assuming that they are random experiments with some sample spaces, right. So you have omega 1 for the first one and capital omega 2 for the second one. So how do I combine them, right? Obviously the combined sample space, right. Now each trial of the combined experiment means what? You have to do both the constituent experiments, omega, otherwise you are not, right, you haven't completed the full trial. So when you talk of combined, you cannot just say I will do one and not do the other, right. So to combine them we form omega 1, this Cartesian product omega 1 cross omega 2. What is the meaning of this Cartesian product? It consists of all ordered pairs, right. So this will be our new omega, where this capital omega has all the ordered pairs, right, of omega 1 and omega 2. So if this one has, let's say, supposing both are discrete and also countable, right, with finite, if this has n1 points and this has n2 points, then the overall omega will have n1 into n2, n1 n2 points, right. So this Cartesian product, I think, so this means ordered pairs, right. The ordering is very important. You can't change it. By convention you have to agree that, right. So I will write here this will, right, the new omega will be something of this form, right, ordered pairs omega, small omega I nu j, where omega I comes from experiment omega capital omega 1 and nu j comes from omega 2. So this is true in the case of, let us say, countable, both omega 1, capital omega 1, omega 2 both being countable, right. And the same kind of thing also happens in the uncountable case as well, right. You can, if you have two random number generators or two spinning pointers, you can, there is no bar on finding or taking a Cartesian product of any two sets, right. So at this point we are just simply combining the two sets, right, capital omega 1, the two sets to form this new set omega, okay. So obviously, for example, if both of them are identical, that is omega 1 and omega 2 are identical, you can get things of the form 1 3 and 3 1, for example, if you do, if you throw dice, right, but 1 3 is not the same as 3 1, that should be very clearly kept in mind, right. 1 3 is getting 1 on the first die and 3 on the second die, or 1 on the first throw, or 1 throw and 3 on the second row, whatever. You are very clear about what the first point refers to and the second one, right. So clearly omega, the cardinality, the number of points in omega, the capital omega is a product if both of these right, are finite, okay. And more importantly now, right, we have to look at the probability that we want to put to right, associate with all these points. So once again right, let me continue here. So let me clearly write out. So omega 1 is basically this new small omega I. Let me say, let omega I 1 n1 and omega 2 be nu j equal to 1 to n2, right. So this is very clear, right, about what capital omega 1, capital omega 2 are, right. And then independently or separately we have, let us say we already give, we start out with some probability assignments to the 2, right. So here we have, let us say, the probability assignments capital P of omega I. These singleton events here, right, have all we already assigned probabilities to them, and here you have, so both of these are assigned, okay. This is anyway our starting point for the discrete case. We have already said that we are going to start by assigning points to all the sample points of the discrete space, right. So now here we have the new point omega I, or the overall the ordered pair omega I comma nu j, and right, and the experiments are known to be physically independent. Then how do we then, right, by independence, right, that is physically independent, the physical independence implying statistical independence, right. Independence is our justification for what? For writing this point, this ordered pair to assigning what probability are we going to assign to this ordered pair? The product of the two. So this is a formal way of saying, well, right, if an experiment consists of tossing a die twice or two dice once, whatever, right, then all 36 points have the same probability. How did you, or 1 by 36, right? How do you get that? Just by invoking this as many times as you want, right? Similarly, right, you don't stop, it doesn't have to stop, it doesn't have to only apply to 2 dice. You can also have a coin being tossed out here and a die being tossed out there, right. There is no bar on what omega 1 and omega 2 can be. As long as it makes some sense to combine them, you can always combine them, right. After all, we are only interested in what we can do mathematically and not whether everything that we do mathematically has some physical meaning or not, right. So, and you can see right, basically this, the only thing you care about is that these numbers should not become negative, right, which obviously they will not, because they are the product of 2 non-negative numbers. And then do they add up to unity? Answer is yes. So it's easy to see that, it's easy to verify. What is easy to verify? That the double summation over I and j of this elementary event, right, will be 1, right. It's like you get a rectangular table of numbers, right, and if you add all the horizontal numbers, you get either nu I or omega j, omega I or nu j, depending on how you wrote the entries, right, and you add them all vertically, so you get all those marginal probabilities, as we will call them later on, right, and the whole thing has to add up to 1, right. So I am not going to, I am going to let you people go and look at this in more detail if you want, right. So now what happens is we have a sample space with n1 and 2 points. Note that omega has n1 and 2 points, right. And therefore, right, if you look at events now, they will be subsets of this omega, right, and you can have that many more events because, right, this 2 power n1 n2 which is the power set of omega is not equal to 2 power n1 into 2 power n2. So note that is bigger, right. So in some sense, right, especially in the discrete case, right, you can clearly see you have more ways of combining the events, right. You can also go back to the event that you see omega I without any concern for the other one, right. That would be the combination of all of these points with omega, where omega is common and nu j is you sum over all the points nu j. If you did that, you would get back probability of omega I. That is, if I have let's say a coin and a die, just to make them different, right. What is the probability of just getting a head? That means you are closing your eye to what is happening with the die, right, if you are only interested in the probability of head. So you will add up head 1, head 2, head 3, head 4, head 5, head 6, you write out all those 6 events, the 6 elementary events for this space, and add them up. If you did that, you would get back the probability of head with, but that does not mean that you are not, I mean that the other experiment is not performed, right. It is, if you look at the samples, the combined experiment, then the understanding is every trial of this combined experiment means both are performed, right. But all these probabilities are also there, it is not that they have gone away, right. This is clear. You can always, you are permitted always to, right, close your eye to what is happening on the other experiment, that's perfectly allowed, right. So this is how basically, right, this is going to be our model for considering combining, right, experiments, right, and I am again going I'm going to go fairly fast over this because I think it's fairly elementary and not particularly. Just the one point to note is that 2 power n1, the power set 2 power n1 n2 is not equal to 2 power n1 multiplied by 2 power n2. So you cannot take the power set, you cannot form this power set by forming, right, the Cartesian product or the product of f1 cross f2, that does not work. This is a point that was actually made by some students long back, so I thought I will include it and right, and also say it out here, right. Why does that happen? Because if I take omega 1 comma nu 2, that event cannot be, or I mean, or omega 1 comma nu 2 union omega 3 comma nu 4 or something, that cannot be formed this way. So you can go and think about it, right, that there will be events in omega which are not expressible in this form. Okay. So this is, right, the basis for constructing more complicated experiments, right, assigning probabilities to the points in it, right, and all of whatever we have said, everything will apply, right. Okay, so as I said, we have to keep moving, right. So what is the next point that we want to look at? Important thing is, of course, the physical independence is, right, often happens, and it always will mean statistical independence, right. Whenever we start with the assumption that we have two different things that are happening, they will be considered to be physically independent. Okay. So this will come up throughout the course. We can always assume that we have any number of physically independent events that are, experiments that are going on, right. There is no shortage of random number generators or spinning pointers and so on, right. After all, we are just hypothetically constructing them, so we can construct any n of them, right. So you can clearly combine more than 2 also. There is no reason why, right, you should stop at 2.